Audio quality check. Audio quality check. Yeah, thank you for confirming. The live chat wasn't actually working for me, so I had to refresh everything. Right. So I'll be waiting here for 2 more minutes. So our today's agenda is that we are going to study how Fourier transform actually comes into action. Right. So we have earlier studied Fourier series. Right. We discussed Fourier series. We discussed how the Fourier series actually originates from very simple integrations, which are actually named the principle of orthogonality for sinusoids, real sinusoids. And from that we actually studied how Fourier series originates, right? Where Fourier series comes from. And today we are going to generalize the idea that we understood, that we realized in Fourier series, and from that we are going to figure out where Fourier transform comes from. So in this topic today, we are going to understand where Fourier transform actually comes from as a generalization of Fourier series. Okay, right? So again, to start, I should tell you that if I have a signal, if I have any signal, and if it has a Fourier series expression, then it also has a Fourier transform expression, right? Because Fourier transform is nothing but a generalization of Fourier series. But if a signal has a Fourier transform, it does not necessarily mean that the signal would also have a Fourier series, right? So we shall learn that, because Fourier transform would be expressed as a generalization or general form, more general form of Fourier series. So that is what we are going to study today. And we are going to also going to look into a very important property of Fourier series, namely the principle of duality, which is pretty useful in evaluating Fourier series for Fourier transform for many rather complicated signals that would otherwise be impossible to calculate the Fourier transform for without actually knowing complex analysis. So that's one of the things we are going to discuss today. And last but not least, we are going to solve a few problems on this domain, right? So with that said, let's I'll be waiting. I'll be expecting a few more people to join. Okay, and we're going to start shortly. So in any case, if you have any question regarding anything we discussed today, feel free to post them on the live chat. I'll be answering all your questions. And right. So again, actually we are diving into complicated mathematics territory, but I shall be trying my best to keep the mathematics or the complexity as simple as possible. Okay, to reduce the complexity as much as possible so that it is pretty understandable for you guys, because I know you are not here to become mathematicians, right? You are here to become engineers. So again, but as engineers, you will learn that mathematics is one of the most important tools that you should understand, right? You should be able to use. So with that out of the way, let's and again we shall continue today's class. We shall be solving examples, we shall be actually calculating Fourier transform, inverse Fourier transform for many different signals, and we shall continue that in the next class as well, right? So in the next class it will be an entire class of working out Fourier transform for Fourier transform and inverse Fourier transform for different signals, right? We shall be doing that. But in any case, today's goal is to figure out what Fourier transform is, where it comes from, and how it actually applies to real life situations, real life signals. That will be our goal today, right? So with that said, again, I'm telling you, if you have any question regarding anything, feel free to ask. Okay. Don't, in my opinion, no question is stupid. So if you think your question is potentially stupid, okay, I never think so, right? Because no question is stupid. You might have a question, might have a query that can actually give others better insight in the subject, right? With that aside, let's start our discussion today, right? So let other people join and we shall continue, right? So if you recall, we left off with Fourier series in the one of the past classes, right? So we left off with Fourier series. Let's recap with that. Okay, let's recall what we studied in Fourier series. So in Fourier series, recall that we actually generalized our expression for Fourier series for any signal, any periodic signal that satisfies the Dirichlet conditions and is periodic with a period of 2t, right? From minus t to plus t. We did something like that. So recall that if xt, which is a signal, say a continuous time signal, is periodic in, I'm saying periodic in minus t comma t, which essentially means that it has a period of 2t. Again, you could consider the period be from minus t by 2 to plus t by 2, but whatever you consider, you have to be consistent with your notation here. This is just a notation. So recall that we considered that xt is periodic in, if xt is a signal which is periodic in minus t to t, this domain, okay, this is an interval, okay, that is xt has a fundamental period of 2t and it can be expressed as a sum of sinusoids as, so yeah, if it has a Fourier series expression, that is what I mean here. Okay, sum of sinusoids as xt that has a DC component first of all, and we have sum of sinusoids, so the even sinusoids and odd sinusoids, n equal to 1 to infinity. So I have an, like instead of cos nt again, I would have cos n pi by t plus bn sin n pi by t, right? Again, 2t is the period, right? Keep that in mind, right? So we discussed that. So if the signal is expressible in this way, then these coefficients can be evaluated this way. A0 can be evaluated as 1 by t integration from minus t to t xt dt, right? We discussed these things in the in earlier classes, right? And we can calculate an, which are the coefficients of the even terms, so coefficients of the cosinusoidal terms, as right? And coefficients of the sinusoidal terms. Right. So yeah, I think these are, I mean, already you people already understood this, right? So I don't think there is any issue. So that is how we express Fourier series for a signal that is periodic with a period of 2t. So periodic in an interval from minus t to plus t, and this is the expression for the Fourier coefficients, right? We established that in one of the one of the past classes, right? So with that said, let's simplify this expression. Let's start simplifying this expression, right? Let's try to understand that this term here, in everywhere we have a term like pi by t. Let's try to understand what this pi by t is, right? This pi by t is representative of the period of the fundamental signal, right? This is representative of the period of the fundamental signal. Try to understand, this capital T is the half period of the fundamental signal, right? So as I said, if this signal for which we are calculating the Fourier series, okay, has a fundamental period of 2t, then the fundamental frequency of the present sinusoids in the signal should also have a period of 2t, right? And so on. So look at the frequency. If the fundamental period is 2t, then what is the corresponding frequency? Then the corresponding frequency, so we call omega naught. We consider that to be the fundamental frequency. What is the fundamental frequency? We express that as omega naught. And what is omega naught? Omega naught would be, of course, 2 pi by, so omega naught is 2 pi by the fundamental period, right? Okay, those who might be confused that this is going to be 1 by pi, no, this is going to be 1 by the half time period. We actually sent you a correction, right? This won't be 1 by pi, it will be 1 by t, right? In the last class we made a few mistakes, right? Not the last class, last to last class, okay? Not a few mistakes, but one mistake, that would be period, right? So for example, if we have a signal which is periodic with a period of 2 pi, the integration would be from minus pi to pi. So from minus half period to plus half period, and divided by half period, okay? So that is the idea here. Same thing. If this signal is periodic with a period of 2 pi, then 2t equal to 2 pi, then t equal to pi, then the integration will eventually become minus pi to pi, and here a division by pi. So right. So what is the fundamental frequency? The fundamental frequency is obviously 2 pi by fundamental period. But what is the fundamental period? That's 2t, for example, in our scenario. So it's pi by t. So whenever we are actually writing pi by t, pi by t, pi by t, we're just expressing the fundamental period of the signal, fundamental frequency of the signal. Of course, the unit is in radian per second, right? So unit is in radian per second. So we are actually expressing the fundamental frequency, right? So this is the fundamental frequency present in the signal, right? So if the fundamental frequency of the signal we are talking about is omega naught, then the sinusoids that compose the signal have a fundamental frequency of omega naught, and subsequently we have higher frequencies like 2 omega naught, 3 omega naught, 4 omega naught, because we have an n here. So in our expressions here, we can safely replace pi by t with omega naught, right? So now we have other expressions like this. So if the signal is expressed as a0 by 2 plus summation n equal to 1 to infinity an cos n omega naught t plus bn sin n omega naught t. Again, we are saying that omega naught t is nothing but 2 pi by 2t, where that is representative of the fundamental frequency of the signal, periodic signal, for which we are actually calculating the Fourier series. So with that said, if this is how it is expressed, then we just have to modify all the expressions, all these expressions accordingly, right? We just have to modify all these expressions accordingly. So wherever we have pi by t, we are going to replace that with omega naught, right? So then we have a representative for the constant term, that would be 1 by t, integration from minus t to plus t, and we have xt. Nothing happens here because there is no frequency term involved here, right? Then we have an. So an would be 1 by t, integration from minus t to t, and xt, and we have cos n pi by t t, but of course pi by capital T would be expressed as omega naught. So n omega naught t dt, okay, and of course we would have bn as 1 by t, integration from minus t to t. So those are the coefficients of the odd terms, so coefficients of the sinusoids. Xt sin n omega naught t dt. So I think this expression is pretty self-explanatory, right? Understandable, pretty easily understandable, right? So now we are going to use this expression. Now we are going to use this expression and see how we can even generalize this expression, because one of the fundamental, so there are a few assumptions while evaluating the Fourier series for signals. So the assumption, one of the three assumptions, the first three assumptions are that the signal has to be bounded. Now, in reality, most of the signals we encounter in real life situations are bounded. Again, another Dirichlet conditions tells us that we have to have a signal that has finite number of extremas, so finite number of minimas or maximas. That is also true for many, most real life signals, right? We won't have infinite number of fluctuations like that, right? And the other condition is that the signal must be bounded. So so it cannot have discontinuities, and if it does have discontinuities, then number of discontinuities must be finite. So the signal can only have finite number of jump discontinuities, finite number of finite discontinuities. So these are the conditions. But the most important condition here is that the signal must be periodic, right? So in order to have a Fourier series for a signal, the signal must be periodic. That's one of the most fundamental criteria here, right? So if I give you a signal which is aperiodic in nature, you cannot really have a Fourier series expression. With that said, try to think about all real life signals. How many real life signals are periodic in nature apart from the power signal that you get at home, right? How many signals are periodic in nature? Say for example, I'm talking, okay, so that's a signal, right? That's not periodic in nature. I'm not repeating myself every now and then, right? So also, whenever you're watching a video, that's a signal. You're listening to a music, that's a signal. But these things are not periodic in nature, okay? They don't repeat periodically. So in reality, almost all signals that you encounter in real life are non-periodic in nature. So the generalization that we are trying to do today with Fourier series is that we are trying to find out what happens to Fourier series when the signals are not periodic in nature. In fact, the signals are aperiodic in nature. Whenever the signals are aperiodic in nature, we are trying to figure out what happens then. Let me increase the audio a bit. I think slightly muted, right? So with that said, let's proceed, right? So these are the expressions we are going to use, right? I don't think there is any issue with that, right? So let's recall what we just did moments ago. So the signal is expressed as this. So a0 by 2 plus summation n equal to 1 to infinity. We have an cos n omega naught t plus bn sin n omega naught t, right? So that's the expression for the Fourier series. So this is how the signal is composed of sinusoids and a DC component, right? So now let's write a0 by 2, no issues with that, plus. Now before we actually proceed, like jump into oblivion for example, let's recall something called the Euler's theorem, right? Let's recall something called the Euler's theorem. Okay, I shall move this aside. Some of you already know this, but let's recall Euler's theorem. So what is Euler's theorem? Euler's theorem says that e to the power j theta is cos theta plus j sin theta. And let me tell you, this is one of the most important and fundamental expressions in mathematics. Okay, and this is a very simple proof. Okay, you don't have to be actually very talented in order to prove this. Okay, but the thing is, this is one of the fundamental and most exciting expressions in mathematics, entire mathematics. So idea is that, so whenever you have a complex exponential like that, e to the power j theta for example, that can be expressed as this, and this can be actually verified by using Taylor series. For example, if you write down the Maclaurin series, if you write down the Maclaurin series for cos theta and sin theta and add them up accordingly, you would get the Maclaurin series for e to the power j theta, and accordingly you can verify this expression. So with that said, we have e to the power, what if we write e to the power minus j theta? Of course, we are replacing theta with minus theta. So I would have cos of minus theta plus j of sine minus theta. That gives me cos theta minus j sine theta. So with that said, what if I add this expression with this expression, right? E to the power. So what if I add these two? Let me pull these even further, right? So what if I add these two? If I add these two, I have e to the power j theta plus e to the power minus j theta, and that gives me cos theta plus j sin theta plus cos theta minus j sin theta. That gives me 2 cos theta, and from that we get cos theta to be equal to e to the power j theta plus e to the power minus j theta divided by 2, and you probably have used these expressions earlier. Similarly, if I subtract these two, e to the power j theta minus e to the power minus j theta, so we are subtracting this from this, then I would have cos theta plus j sin theta minus cos theta plus j sin theta, so I would have 2j sin theta. So basically we have an expression for sin theta as complex exponentials. So e to the power j theta minus e to the power minus j theta. Right. So we have an expression like that. So I believe all of you already knew that. So with that said, but why did I tell you this? I made you recall this expression because we are going to just shortly put that expression, those expressions here. So we have a summation here, right? So we have n equal to 1 to infinity, and we have a n, and then instead of cos n omega naught t, where I am considering n omega naught t to be theta, instead of writing cos theta, I am going to use the expression of complex exponentials. So here I am going to write e to the power j n omega naught t plus e to the power minus j n omega naught t divided by 2. Recall that this a n is multiplied with everything, and plus b n multiplied with e to the power j n omega naught t minus e to the power minus j n omega naught t. Right? That's a valid expression for the Fourier series, right? We have just expressed everything as complex sinusoids, right? So these are complex sinusoids, right? Complex exponential forms. Right. Right. So with that said, can we simplify this expression further? Of course we can. So I can write this as a0 by 2 plus. Now try to understand that this 1 by j has a very important property, because we already know that 1 by j, we know that j square is equal to -1, right? So 1 by j is basically minus j, right? So we know that, right? Just since j square is equal to -1, so we know 1 by j is equal to -j. So again, j is the complex unity here. So with that said, this can be written as n equal to 1 to infinity an. Okay, why don't I copy everything? Right, good. And I'm taking this 1 by j, pulling it here. So, and I'm making that minus j bn. So I don't think there is any issue with that, right? This is easy to understand, right? Pretty simple, I think. So with that said, let's simplify this even further. So again, our goal is to generalize our expressions, so keep that in mind. Now here, if we just divide everything up and then try to simplify, try to see, we have these terms, right? E to the power j n omega t, and then again e to the power j n omega t. And what are the coefficients of e to the power j n omega t? That's a n by 2 and minus j b n by 2, right? So if we take e to the power j n omega t common out of that, so let's simplify, and then we shall do it. So we have a n by 2 into e to the power j n omega naught t plus a n by 2 into e to the power minus j n omega naught t, and then we have, with this we have minus j bn by 2 e to the power j n omega naught t, and then we have plus j bn by 2 e to the power minus j n omega naught t. We have this expression, right? And if we now combine this term with this and this term with this, let's see what we get. So we have a0 by 2 plus summation n equal to 1 to infinity, and we have here, we have an minus j bn by 2 into e to the power j omega naught t, right? Try to follow, and if you have any query, please feel free to ask. And we are combining this term with this term. We have an plus jbn by 2, and we have e to the power minus j n omega naught t, right? Right. We have this expression. It might seem like instead of simplifying things, we're actually making things unnecessarily complicated, but rest assured that this will be resulting into a very simplified form eventually. Oh yeah, sure, absolutely, prompt response, right? Thank you. Right. So if you can point out the mistakes I make, it essentially means that you're actually following correctly, following properly. So now let's remember this expression, right? This expression is eventually the expression for xt, right? This is still xt, right? This is still the expression for xt. So remember this expression, don't forget it, okay? right? Right. So with that said, let's consider this expression, this, right? This. So what is this? We have an minus jbn by 2. Okay, and let's name it, like engineers, let's name everything. Let's consider that to be something. Now look at this expression. Okay, this is like a0 by 2 plus summation something into e to the power j theta. And what is e to the power j theta? What is this term? This is known as the complex sinusoids, and as electrical engineers we have used these terms over and over again, right? So we use this kind of expression to express sinusoids, right? Complex sinusoids. So these are nothing but sinusoids, right? This is one kind of a sinusoid, this is another sinusoid. So it is like the Fourier series expression we had earlier, like an cos n omega naught t plus bn sine omega naught t, but instead of that cos and sine, we have some complex sinusoidal terms present with us. So these can be considered to be complex Fourier coefficients, right? So this is a Fourier coefficient, but only a complex Fourier coefficient. Okay, so instead, now with that said, let's consider the complex Fourier coefficient to be xn, right? So again, this is representative of the n into omega naught radian per second term, right? So this is the complex coefficient for that particular scenario. So now with that said, that's half an minus j bn, but writing that is completely futile. What is an, what is bn? You already know that. What is an? An is 1 by t, integration from minus t to t, okay, xt cos n omega naught t dt, and we have minus j bn. And what is bn? Again 1 by t, integration from minus t to t xt sine n omega naught t dt, like that. I think that's clear, right? We have just put the expression for the Fourier coefficients in here. So now we can take 1 by t out of this. If I take 1 by t out of this, so we have 1 by 2t, and we have this integration. Now see, try to understand that we can actually combine these two integrations into a single one, because we have xt cos theta, something like that, and xt sine theta here. Okay, and along with that we can combine them and write it as this integration from this, and we have xt as common, and we have cos n omega naught t minus j sine n omega naught t dt. Right. So is there any confusion with this? I don't think there is any confusion with this, right? Because this is as simple as it can be. Now again, recall, what is this expression? What is this expression? What is this expression? What is this expression? This expression is cos. This expression is e to the power minus n omega naught t, right? This expression is minus e to the power minus n omega naught t, right? J n omega naught t. So I have 1 by 2t, integration from minus t to t xt e to the power minus j n omega naught t dt. Because try to recall that e to the power minus j theta was cos theta minus j sin theta, right? So that's the expression for xn. So please try to understand this first. Yeah? Okay. So if that is xn, again try to remember this, don't forget this just yet. Try to remember this. If that is xn, let's now again go back and figure out what would this expression be, x of minus n. So of course we are now introducing a term for, so let's recall that. So we are now introducing negative frequencies. So now negative frequency might sound pretty weird for generic people, but for electrical engineers we understand that negative frequencies are nothing weird, right? Negative frequencies can be considered to be frequencies, but when the signal is rotating in the happening in the opposite direction, opposite time direction, for example, right? Something like that. For example, if something rotates in the clockwise direction, and if you consider the frequency to be positive, then if the system if the object rotates in the anti-clockwise direction, you can consider the frequency to be negative, right? Something like that. So if we introduce the terminology for negative frequencies, then instead of having just positive values for n, we can also have negative values for n, right? So if we introduce that, and with that said, if I try to express x of minus n, we have, try to understand what is x of minus n. X of minus n, if you recall here, okay, that's xn, right? Now x of minus n would be simply a of minus n minus j b of minus n divided by 2. We're just replacing n with minus n. So a of minus n minus j b of minus n by 2, right? Now recall this. What is an? Rather, what is a of minus n? A of minus n, again from the expression for an, would be this. Now instead of n, I would have a minus sign here. So let's clear this up. So that would be a of minus n. And since this is a cosine, this minus sign automatically cancels up. So it becomes integration from this xt simply cos n omega naught t dt. And what is this? This is nothing but an, right? And again, this is another, what should I say? This is another indication that this is representative of the even terms present in the Fourier series. That's an. So a of minus n is nothing but equal to an. And what about b of minus n? B of minus n would be this. We have sinusoidal term, and just instead of writing n, we're writing minus n. And if we simplify this expression, again, since we have a minus sign inside this, and this is a sinusoid, of course the minus sign will automatically come outside, because sine of minus theta is minus sine theta, right? So integration from minus t to t, we have xt and sine of, yeah, n omega naught t dt, and that's basically b of minus bn. So we just moments ago wrote x of minus n. What was that? X of minus n. It was a minus n minus j b minus n divided by 2. So it is a minus n minus j b minus n divided by 2. But we just realized that a minus n is just an, and b minus n is minus bn, right? But now let me copy paste something we wrote earlier. Let me copy paste this expression. Let me copy this and paste this here, right? So now recall that we considered this expression to be xn, right? Now let's write this a0 by 2 plus summation n equal to 1 to infinity, because we express this as xn, that is why we started, right? So this is xn e to the power j n omega naught t. But what about this? What is this? Recall, moments ago we realized that this is x of minus n, right? So plus x of minus n, we have e to the power minus j n omega naught t, right? So now things are looking slightly more promising here. But let me now teach you for a moment about summations, right? About summations before we actually proceed. Again, this is going to be completely an ad hoc discussion. Again, I'm going to erase this discussion moments after saying this. So try to understand. If I write summation, okay, and n here, I'm writing n equal to 1 to, say for example, infinity. What does it give you? It gives me 1 plus 2 plus 3 plus and so on up to infinity, as long as it goes. Right? No problem with that. Is there any problem with that? No, I don't think so, right? So what about a minus sign here? So if I say n equal to minus 1 to minus infinity and an n here, so what does it tell you? I'm doing this minus 1 plus minus 2 plus minus 3 and so on, right? These are all the same, right? I think this is understood, right? Now what if I tell you, what if I ask you about this one? So I'm integrating from 1 to infinity and on minus n. So what would that mean? That would again mean that I'm putting n equal to 1, n equal to 2, n equal to 3 and so on and summing them up. So if I put n equal to 1, I get minus 1, sum. N equal to 2, I get minus 2, sum. N equal to 3, I get minus 3, sum, and so on. So with that said, look very carefully that these two summations are identical in nature. So as a matter of fact, summation n equal to minus 1 to infinity on n is identical to summation n equal to 1 to infinity on minus n. I think that's understood. And with the same understanding, we can say summation n equal to minus 1, summation n equal to minus 1 to infinity on any function of n is equal to summation, sorry, minus infinity, this is minus infinity. N equal to 1 to infinity function of minus n. Right? Because here I'm putting 1, but since we have a minus n already, it's becoming minus 1. Then I'm putting 2, it's becoming minus 2. Then I'm putting 3, it's becoming minus 3. And so on, I'm going up to minus infinity because we have a minus n here. And here I have a plus n here, but since the limits are like that, so I'm putting minus 1, minus 2, minus 3 and so on, and then summing up. So these two are identical, right? So if you understood that, then we can actually proceed, right? I can get rid of everything here. And now, why did I tell you? Of course, we have something like that here, right? A0 by 2 plus. Now I am splitting this integration, splitting this summation, sorry. So I have xn e to the power jn omega naught t, and we have a plus summation n equal to 1 to infinity. We have x of minus n e to the power j minus n omega naught t, right? You might have already guessed what I'm going to do next. It's going to be a0 by 2 plus summation n equal to 1 to infinity xn e to the power jn omega naught t, and this looks like we have minus n everywhere, right? So this can be written as n equal to minus n to infinity, sorry, minus n to minus infinity, and xn e to the power j n omega naught t, right? This was the function of minus n, so these two are identical in nature. Let me know if you did not understand that. Okay, this is what we discussed just moments ago. Right? Again, recall what we are trying to find out. We are just expressing xn. Okay, we are still expressing xn, writing expression for xn, right? So if that is understood, let's try to figure out what x0 is. But what about x0? We're talking about all these, but what about x0? Again, what is the expression for xn? The expression for xn we wrote earlier. Where was it? Yeah, this is the expression for xn, right? So it's 1 by t integration from minus t to t xt e to the power, was it a minus sign? Yeah, minus j n omega naught and t, something like that. Now of course n is a 0 here, for example. Oh, repeat which last part? Repeat this part? Right. So if you're saying if I have to repeat this part, try to understand that this thing here looks like this thing, right? This thing here looks like a function of minus n, right? So we are summing over n equal to 1 to infinity plus infinity over a function of minus n, right? So this is summation n equal to 1 to infinity on f of minus n, and this is summation n equal to minus 1 to minus infinity over a function of n. Instead of plus minus n, we are having plus n here. And moments ago I told you earlier that this and this are identical in nature, because here we are just putting minus 1, minus 2, minus 3 and so on, and here we are putting 1, 2, 3, 4, but eventually we have a minus sign inside, so that makes it minus 1, minus 2, minus 3, minus 4 and so on, right? So I think you got that right. So if I do that and put n equal to 0, of course n equal to 0 gives me 1 here, right? So this entire expression becomes a 1, so I have dt here, right? But what is that? That's of course a0, right? That's a0. So with that said, we have this expression, right? This expression. What is that expression for? That expression is for xt. Therefore xt is equal to, instead of writing a0 by 2, and I am now writing x0 by 2, because that is what x0 is, plus summation n equal to 1 to infinity. I have xn e to the power jn omega naught t plus summation n equal to minus 1 to infinity. I have minus 1 to infinity. I have x of minus n e to the power minus j what am I doing? xn e to the power j n omega naught t. So we have just written this expression, this thing, and instead of writing a0, we have written x0, because we just moments ago realized that a0 is nothing but equal to x0. So I don't think there is any problem with this. Please feel free to ask if you have any query regarding anything we have discussed so far. So I have x0 by 2 plus. Now try to understand something very important here. That what are the points we are looking for? What are the points we are integrating for? Right? Try to figure that out. Try to look into that first. Okay, what are the points we are actually integrating for, right? Okay, so okay, let me just go back for a moment. Okay, we had a 2, right? But again, we were going to make a mistake, right? What is xn? Xn was had a 2t, right? Wait a second, right, it has a 2t. That was the expression for xn. Recall. We had xn equal to this. We had a 2 here, e to the power. So that was the expression for xn. So we evaluated xn as 1 by 2t in this integration, right? Right, 1 by 2t, we had a 1 by. So we had minus j n omega naught t and dt. Oh, we have this expression. We had this expression. So try to figure out that. So x0 would have been this. So this becomes 0, so that becomes 1. So we have a dt here. Okay, so that's not a0 by 2. That's not a0. That's a0 by 2, right? Since a0 is this integration, but instead of dividing by 1 by 2t, we divided by t. So that's a0 by 2. So I think that's right? Because a0 we already know that this integration just right. So this was the expression for x. So yeah, so we made a mistake here. So that has to be x0. Again, if you did not get it, please let me know. That has to be x0, right? Right. Because in the expression for xn we had a 1 by 2. Right. So with that said, that's x0. But what about x0? x0 can be written as x0 e to the power j0 omega naught t plus. Now look at these summations. Okay, right? So in these summations, what am I doing? So I am putting 1, 2, 3, 4, 5, 6 and so on. So x1 and then x2 and then whatever, right? And in this summation, what am I putting? In this summation, I am putting minus 1, minus 2, minus 3, minus 4 and so on up to minus infinity. That has to be minus infinity. Yeah. Up to minus infinity. So we have all the values, right? We have n equal to 1 to plus infinity, n equal to minus 1 to minus infinity, and also n equal to 0. So this is representative of n equal to 0, right? So we have n equal to 0 and then plus 1 to plus infinity and minus 1 to minus infinity. So essentially we are summing from minus infinity to plus infinity, including 0, right? In between. So it starts from minus infinity, goes up to minus 1, and then we have 0, we have 1, and we have up to infinity. So this entire summation can be simply written as, because we are just going through all the possible values of n, starting from minus infinity up to minus 1, then at n equal to 0, and then from n equal to 1 to plus infinity. So we are considering all the values of n. So n is actually starting from minus infinity. And again, since we're just summing terms, adding terms, it does not matter in which order we add terms, because addition is commutative in nature, right? So, right, and we can write xn e to the power jn omega naught t, right? Right, combining all these terms. So xn actually varies from negative infinity to plus infinity, considering all the integers. Here you have to understand that n belongs to the set of integers. So n is integer. N are all representative of integers. Okay, so we are representing positive frequencies, negative frequencies, and zero frequency. Zero frequency means DC component. N equal to 0 means zero frequency, which is the DC component. So we have xt as this, right? And this expression is known as the complex exponential Fourier series. So this is again the Fourier series expression, xt equal to summation something like that, summation of sinusoids. But this is now the complex exponential form of Fourier series. Okay, x0 goes in between. Okay, x0 goes in between. So if you start counting from minus infinity to plus infinity, say you start counting from minus 10 to plus 10. Say you're counting from minus 10 to plus 10, right? So minus 10, minus 9, minus 8, minus 7, minus 5, minus 7, minus 6, minus 5, minus 4, minus 3, minus 2, minus 1, 0. Then 1, 2, 3, 4, 5, 6, and so on. So we have a 0, right? N equal to 0 in between, right? So that is where x0 goes, because x0 is nothing but x0 into e to the power j0 omega naught t, right? So that is representative of x0 here. Yeah. So since we are counting from minus infinity to plus infinity, of course not from minus 10 to plus 10, right? That's called the complex exponential form of Fourier series, or sometimes just called the exponential form of Fourier series, or the complex form of Fourier series. I like to call it the complex exponential form of Fourier series, right? So I don't think there is any issue with this. So try to understand, by going through so many complicated steps, we have actually simplified everything. Now instead of having a big expression, we have a small expression. We have this expression. And what are the Fourier coefficients? And the complex Fourier coefficients are just xn. Now instead of three different things like x0, like a0, like a0, an, and bn, we just have xn, right? And that's 1 by 2t integration from minus t to t xt e to the power minus jn omega naught t dt, right? So instead of doing instead of summing three different things like a0 by 2 and then an cosine terms, then bn sine terms, okay, we have this as the expression for the Fourier series for the signal. Okay, again we are dealing with the same signal we started with, and these are the Fourier coefficients. So everything is represented by this. Every single thing in the Fourier coefficients are represented by this, right? So this is the expression, right? So this is the Fourier series expression, and this is the corresponding, these are the corresponding Fourier coefficients. So now we have boiled down into, from three different integrations, we have boiled down to one integration, and three different summation things we have now boiled down to one, just one. So that is how we have simplified into the complex exponential form of Fourier series. Okay, I'll be waiting here for 2 minutes or 3 minutes to for you to ask any question that you might have, because shortly from this we are going to jump to Fourier transform, right? Because this is where we end Fourier series and start looking into more generalized expressions. So if you have any question, feel free to ask. I'll be waiting here for 2 minutes. Okay, feel free to ask. Let me come back and I will answer your questions. So I'll be waiting here for 2 minutes. So consider that a break, for example. Okay, but don't leave the stream, please. Okay, we'll be coming back shortly in 2 minutes. Okay, all right. So we have a question. We have a few questions. One of the question is that how x0 becomes equal to a0. No. X0 is not equal to a0. X0 is actually a0 by 2. Okay, so here let's put n equal to 0. If you put n equal to 0, we have x0 and 1 by 2t integration minus infinity to minus t to t, and we have xt. And when I put n equal to 0, what do I get? I get e to the power 0, right? So, okay, I'm answering your question. So that's it, right? But this is like 1 by 2 into 1 by t integration from minus t to t xt dt, and that's your a0. So it's a0 by 2, right? I think that's okay. So one of you asks, x0 was not alone. It has a divided by 4 and also does not have so it doesn't make any change. Yeah, x0 does not have, yeah, that's what I told you, right? X0 does not have here, try to understand, x0 does not have any term like that, e to the power term. But that doesn't matter, because if you keep on counting, when you reach n equal to 0, what do you get? You get x0 e to the power 0. Okay, that's just x0, because e to the power 0 is 1, right? And there is no divided by 4. Try to look through this. I shall be sending you the handouts, of course. Try to look through the handouts. There is no x0 divided by 4 anywhere. Okay, apart from that, if you have any query. Yeah, let me get rid of this. So the dogs are here actually doing a meeting on coronavirus. Right. So time for the generalization we have been talking about. Okay. So what generalization am I talking about? I'm talking about the generalization where we do not discard the Dirichlet conditions. Of course, we cannot discard Dirichlet conditions because those are inherent here. Yeah. The Dirichlet conditions are inherent within the Fourier series and Fourier transforms. So in order to have a Fourier series or a Fourier transform, the signal must satisfy, okay, again this is a sufficient condition, but the signal must satisfy the Dirichlet conditions. But the signal may or may not be periodic, but because earlier I told you that most of the signals we encounter in real life are not periodic in nature. Like even the simple step signals, like switching on a power supply, okay, switching on a DC power supply, for example, that's a step signal, that's not periodic. I'm talking here, that's not periodic. Okay, so most of the signals that almost all the signals that you encounter in real life are not periodic in nature. They do not repeat after periodic intervals. At least most of them do not, right? So with that said, let's consider aperiodic signals and try figuring out what happens when we have an aperiodic signal. So aperiodic signals. So what are aperiodic signals? Aperiodic signals are those signals which do not repeat themselves after a certain interval, right? Which do not periodically repeat themselves after a certain interval. But again, in mathematics, this is the idea. If we have an aperiodic signal which does not repeat itself after a certain interval, we can always assume that the signal would probably change if I give it enough amount of time. Would probably repeat itself if I give it enough amount of time. So this is the idea. Okay, the idea is I'm saying, okay, I'm talking here. I'm not repeating myself, right? I'm not repeating myself, right? So in this entire class, I haven't repeated myself, probably, right? So whatever I'm saying, I'm not repeating myself. So my signal here is not a periodic signal. It might appear so, right? But if you come back 1 year later, you would see that I am teaching the same thing once again. So I would be repeating myself after a very long amount of time, right? After 1 year, probably. Okay, if after 1 year I'm still teaching signals and systems, I'll be repeating myself. But I'm not repeating myself right now, right? So in mathematics, the idea is if I give you an aperiodic signal, okay, the signal might seem aperiodic if you don't give it enough amount of time. But theoretically, if you give it enough amount of time, the signal could probably repeat itself. That is the idea, right? So idea is whenever you are standing on the ground, the earth looks flat. That is the idea. Okay, but if you are if you are standing on a very high altitude, for example, okay, and if you are looking at the earth from say for example a few thousand meters above, it won't feel like a flat surface, right? Something like that. Okay, so the idea is if you give an aperiodic signal enough amount of time, that signal might repeat itself. Okay, and what is enough in mathematics? Nothing is enough other than infinity, right? So the idea is if you have an aperiodic signal and if you give it infinite amount of time, you can consider the signal to be periodic. Again, let's I'm giving you time to wrap your head around the idea. Okay, so we consider aperiodic signals as periodic signals. But t, which is the representative of period, is infinite. So just like I said, I'm not repeating myself right now. Okay, probably you won't be seeing me repeating myself. But if you come back 1 year later, okay, and somehow join the class like that, you'll be seeing that I am teaching you the same thing once again. Okay, so I'll be repeating myself after seemingly an infinite amount of time. So anything that is aperiodic can be considered periodic if I consider the period to be infinite. So that is the mathematical idea behind aperiodic signals. And we are going to use this generalization in our expression for Fourier, our expression for Fourier series in order to obtain Fourier transform. Again, periodicity is a very specific property of a signal, right? Okay, so any expression that we derive or any mathematical tool we obtain for aperiodic signals, okay, so if we have a mathematical tool, okay, that works on aperiodic signals that do not assume the periodicity of the signals, okay, then that tool will also be applicable on signals that are periodic in nature. Try to understand. Okay, periodicity of a signal would give us some extra benefits. Okay, but if the signal is aperiodic and we have a tool for analyzing aperiodic signals, then that tool which can analyze aperiodic signals will most certainly be useful or be able to analyze periodic signals as well, because with periodicity we're just introducing yet another constraint on the signal, right? So periodic signals are nothing but a subset of aperiodic signals, right? So that's the idea. So Fourier transform, a signal might have a Fourier transform but might not have a Fourier series. But if the signal has a Fourier series, it must have a Fourier transform as well. So with that said, I think I got the idea through to you. Let's look at this expression. Let's look at this expression very carefully. Okay, if I look at this expression, okay, let me just copy paste this expression once more, because copy pasting is what we do. Right. In this expression, try to understand. we are saying that the period is going to this, right? So if that is the assumption, let's go back. What was omega naught? Omega naught was 2 pi by 2t, okay, right? By 2t is the period. Recall, 2t is the period, right? So that was pi by t. No confusion there, right? But what am I saying here? I am saying that t is a very large quantity. Then what happens to pi by t? Pi by t becomes a very small quantity, right? Right? So that would basically become a very small frequency quantity. In fact, an infinitesimally small frequency quantity, right? So instead of writing omega 0, the fundamental frequency, I will be writing d omega, because now omega naught is actually becoming d omega. So so this is infinitesimally small. So omega is now infinitesimally small, so I'm writing d omega. I don't think there is any problem with that, right? So I have d omega equal to pi by t. Okay, no problem with that. So of course, with that said, let's have that. Okay, let's have that. Please let me know if you still have any query regarding any of these. Okay. So look at this one. What about d omega? D omega is a very small frequency, right? Try to understand. D omega is a very small frequency. But before I go into that, let's consider this. Let's consider omega 0 is equal to 1, right? So 1 radian per second. So what is the frequency present in the signal? 1 radian per second, and then all the overtones of that, right? So 1 radian per second, 2 radian per second, 3 radian per second, all the harmonics. 1, 2, 3, 4, 5, 6, and so on, because n is increasing like that, right? Right? So the frequency we are talking about are 1, 2, 3, 4, and so on, right? That's n omega naught, right? So that's omega naught, 2 omega naught, 3 omega naught, 4 omega naught, and so on. These are the frequencies of the sinusoids present in the signal. Now what if omega naught is smaller, say 0.5 radian per second? Then I would have, of course, understandably, 0.5, 1, 1.5, 2, and so on, right? So try to understand that if, say, for example, this is 0.1 radian per second, okay, radian per second, then we have 0.1, 0.2, 0.3, 0.4. So the gap between the frequencies of the sinusoid present in the signal is actually reducing, right? So the gap between the frequencies of the sinusoids present in the signal are reducing. So when the fundamental frequency was 1 radian per second, then the gap between the sinusoids, gap between the frequencies of the sinusoids were 1 radian per second. Now when the fundamental frequency is half radian per second, then the gap between the sinusoids are half radian per second, right? Then when the fundamental frequency is 0.1 radian per second, then the gap between the frequencies of the fundamental signal, gap between the frequencies of the sinusoids present in the signal are 0.1 radian per second, and so on, right? So what if the frequency is too small? Instead of omega 0, I have a very small frequency, right? So this is going to be d omega, this is going to be 2d omega, this is going to be 3d omega, this is going to be 4d omega. But what are those? Now d omega is a very, very small quantity, infinitesimally small, right? So now what happens is that this gap between d omega and 2d omega is so small that they can be considered infinitesimally apart. What is the gap between them? The gap between them is extremely small. So here frequencies are discrete in nature, right? Try to understand, frequencies are discrete in nature, but the moment we consider t going to infinity, we have frequencies that are no longer discrete in nature. The frequencies, the individual frequency components, right? The individual sinusoidal components have frequencies that are so close together, okay, that the frequency expression, the frequencies can be considered a continuous function instead of a discrete function, right? So the signals that are aperiodic in nature technically would have every possible frequency present in it, okay, no matter how small in magnitude, every possible frequency has the potential of being present in that, right? Because omega naught is so d omega is so small, okay, and again n actually goes to infinity, right? So we have a very small time span, say for example frequency span, say for example 0.0001, then the next frequency would be 0.0002, 0.0004, 3, and so on. So you essentially have a full spectrum of frequency. So what happens is, instead of the frequencies being discrete variables, the frequencies are now a continuous variable, okay? What are discrete variables? Like 1, 2, 3, 4 variables that have a finite gap between them. Now these do not have a finite gap between them. The gap is infinitesimally small, basically very, very small. So what I am saying is, when the fundamental period goes to infinity, which means when I am considering the aperiodicity, whenever I am considering aperiodic signals, then omega naught goes to d omega, becomes d omega, right? And what happens to n omega naught? And what happens to n omega naught? N omega naught is now representative of a continuous span of frequency. We express that simply with omega, right? Because on the omega scale, we are considering very small points that are very close together, and I'm going through them. So because this is 1 d omega, 2 d omega, 3 d omega, 4 d omega, and so on. And d omega is so small that we're actually spanning the entire frequency spectrum, right? So that is the simplification, or that is the generalization we are actually doing here. So please let me know if you have any confusion understanding this idea here. So again, we are considering the period, okay, to be going to infinity. Again, this is half period, but yeah, nonetheless. So we are considering the period going to infinity, and from that we are considering that the frequency becomes infinite, the fundamental frequency becomes infinitesimally small, extremely small, but not zero, but extremely small, okay? And apart from that, we have expressed this n omega naught as omega as a continuous variable. So these are discrete frequencies, and this is a continuous variable in frequency. So please ask me if you have any query regarding any of these. Please feel free to ask if you haven't understood this idea, or please confirm if you have understood. Right? So let me just copy paste this. Please let me know if you have understood. Please let me know if you haven't understood. So let me copy paste this. right? So if you have understood, so let me copy paste this. Okay, right, right. So I'm saying with t tending to infinity for aperiodic signals, now we are calculating this xn divided by d omega. Now try to understand what is xn divided by d omega. These are the let's write down. So Fourier coefficients Fourier coefficients per unit frequency. Okay, Fourier coefficient per unit frequency expressed as xn divided by d omega, and you will shortly know why I'm doing this. So xn by d omega, that would be 1 by d omega, and xn, of course. What is xn? Xn is 1 by 2t, 1 by 2t, and on this let me clear this up. Okay, we have a limiting scenario, right? We have 1 by d omega, and we have 1 by 2t, integration from minus t to t. And again, don't be afraid of this mathematical complexity here, because I'm trying to explain everything, so don't worry. If you encounter anything that is unexplained, I will explain it. Please feel free to ask. So it is minus j n omega naught t and dt, right? Right. So what is 1 by d omega? Let's recall. What is 1 by d omega? Right. 1 by d omega would be t by pi, right? So 1 by d omega would be t by pi, right? So we are going to put that here. So limit t tending to infinity, we have t by pi into 1 by 2t, integration from minus t to t, we have xt, and e to the power minus j n omega naught t dt. So we have limit t tending to infinity 1 by 2 pi. So we have 1 by 2 pi because we're just cancelling t here, and integration from minus t to t xt e to the power minus j n omega naught t dt. And now we are going to put the limits. So if I put t tending to infinity, so I have 1 by 2 pi here. So integration from minus infinity to plus infinity, because we have just put the limit here. So t tending to infinity. So that limits now become minus infinity to plus infinity. And this is again understandable because this is one complete period of the signal. So the entire behavior of the signal was previously captured between minus t to plus t, because the signal repeats itself after every 2t interval. Now the signal does not repeat itself. So in order to capture the entire essence of the signal, I shall be needing to integrate from minus infinity to plus infinity. So I shall be needing to look at the entire signal instead of looking at a single period of the signal. For a periodic signal, looking at a single period of the signal was sufficient, but this is not true any longer. So, and this is quite understandable that way. So we have xt e to the power minus j, and instead of n omega naught, moments ago I told you n omega naught was a discrete frequency term. Now since t is becoming infinite and omega naught is becoming infinitesimally small, this discrete frequency term n omega naught is now becoming simply omega, right, which is a continuous frequency term. So I would have j omega t dt. Again, what have I been calculating? I have been calculating xn by d omega, right? Those are the Fourier coefficients per unit frequency. Those are the Fourier coefficients per unit frequency. So please let me know if you have understood this far. If you have understood this far, please let me know. Right. Right. So with that said, what happened to the original expression for the signal? So the Fourier series expression, what was the Fourier series expression? Was xt, moments ago we derived this, n equal to, sorry, not n equal to, huh? Since I am mathematically inclined, I can never write equal to infinity. Okay, because writing equal to infinity is mathematically illegal. Okay. What was it? Let me go back, because I am very bad at remembering expressions. Right, it was e to the power j n omega naught t. Right, so that was the Fourier series expression, right? That was the Fourier series expression. I don't think there is an issue with that. Now, what about this summation now? Look at this summation. Try to understand that now xn was a function of omega naught, right? So xn was a function of omega naught, understandably, right? So xn was a function of omega naught, and now omega naught does not exist really, right? Because omega naught, n into omega naught has been reduced to omega, which is a continuous variable, right? So try to understand that I can actually write something like this, like I have xn and d omega, and I have this, instead of n omega naught I have omega and t, and I have d omega here, right? Something like that. And understandably, this is no longer a summation, because for the summation it meant that we had discrete points. Now n does not separately exist anymore in reality. Okay, n does not separately exist anymore, because look at the expression for xn divided by omega. In the expression for xn divided by omega, n no longer does exist, right? N no longer exists. So if n does not exist in that expression, then this cannot be summed over n, because now n, this entire terminology of n and omega naught, has been combined into the terminology for omega. So this summation essentially becomes an integration, right? And again, what is integration? Integration is nothing but summation when you take very close by points, right? When omega is discrete, it's a summation. Now since omega is continuous, it's an integration from minus infinity to plus infinity. So I think this is understood, this term, because xn by omega, even though I'm writing it as xn by omega, this is no longer a function of omega. This is not a function of n, not a function of n. This is no longer a function of n, right? So that is the expression we get. So from this we have this, right? Again, what is integration? Integration is nothing but summation, nothing but a summation over infinitesimally small spaces, right? Infinitesimally small variables. So like that. So since we have made it infinitesimally small, we reduce this to this. Please let me know if you have understood this. Right. And today probably we shall not be having any time left for doing any solving any examples, solving any problems. So, and I shall not be exceeding I shall not be making it, I shall keep it between like 100 minutes. Okay, so let's hope that we shall be ending the class shortly. So we shall be solving plenty of examples, don't worry, in the next class that we shall be scheduling on this Friday. So yes, don't worry about the solve problems. We shall be solving plenty of those. But try to understand where Fourier transform comes from. And again, please let me know if you have any, if you don't understand this, right? Where this integration comes from. This integration is coming from the fact that this is no longer a function of n, and n omega naught has been clobbered into omega, which is a continuous variable. Right. All right. So going into that, let me just go back here. So we have an integration sign, infinity to infinity, and we have e to the power j omega t d omega, right? And here xn by d omega, what can I write it as? So xn by d omega is 1 by 2 pi. So 1 by 2 pi integration from minus infinity to infinity xt. Let me erase this. I don't have spaces. So right. So integration from minus infinity to infinity. Right. So I'm leaving a space for this, and we have e to the power j omega t d omega, and xn by d omega is 1 by 2 pi integration from minus infinity to infinity xt e to the power minus j omega t dt. Right. So please let me know if you have understood this properly. So we just expressed xn by, we have just put xn by d omega as the expression we derived. So again, what are we calculating? We are calculating xt, right? So this is just xt. We are writing the expression for the Fourier series, right? This is just xt, right? So in a sense, that is what it is, right? So now look at everything here. So if we just express this in a slightly easier fashion, so this term I'm just keeping this 2 pi here. Okay, I can do that. Look at this. This is a function of frequency only, because try to understand, we are integrating with respect to time, and after integrating with respect to time, okay, time will not be remaining, right? Because this is a definite integral, namely an improper definite integral, improper integral, but nonetheless it's a definite integral with respect to t. Basically, after evaluating everything, we shall be putting the limits for t, and subsequently t will not remain. So this entire thing is a function of frequency. This entire thing is a function of frequency. This is an entirely function of frequency, right? This is entirely a function of frequency. And while we are at it, let's bring this 1 by 2 pi outside here. This is entirely a function of frequency, okay, and we call that x omega. So if I consider that to be x omega, then what expression do I have? I have xt is equal to 1 by 2 pi integration from minus infinity to infinity x omega e to the power j omega t d omega, right? Let me bring it to this. Therefore this, right? So in this expression we have just put x omega here. We have just assumed that this is x omega because this is going to be simply and entirely a function of omega. So this is where x omega is this integration inside. So integration from minus infinity to infinity xt e to the power minus j omega t dt. And believe me or not, we are at the end of today's class, because this is known as the Fourier transform pair. This is called the Fourier transform. And this is known as the inverse Fourier transform. Right? These two combined give you the Fourier transform expression for Fourier transform, right? Right. So let's recall what we just did. Okay, we now have a signal xt that does not need to be periodic, but all the frequency properties is now embedded within this. So xt does not have to be periodic, but it does need to satisfy the Dirichlet conditions. And if it does, then all the frequency properties, all the frequency component, all the different sinusoidal components can be expressed through this function. And if we have this, then we can do this integration to get the signal back, right? So in essence, this is the Fourier series expression, like that summation, right? This is that same expression, like that summation, that particular summation that we do with Fourier series. And these are all the Fourier coefficients per se, right? So in essence, calculating the Fourier transform is nothing but calculating the Fourier coefficients for an aperiodic signal, right? And calculating the inverse Fourier transform is nothing but taking those Fourier coefficients and getting or writing an expression for the original signal in terms of sinusoids. Let me repeat myself. Fourier transform, or this, can be simply thought as calculating the Fourier coefficients for an aperiodic signal. And calculating the inverse Fourier transform can be assumed or can be imagined as such as we are taking the Fourier coefficients and writing an expression for the signal in terms of sinusoids, right? So this is the expression for the Fourier series, like that summation thing, and these are all the Fourier coefficients, like those integration we get from the Fourier series. So those are the expressions. This is called a Fourier transform pair. Okay, there are three other possible pairs. Okay, this is one of the pairs. There are four other pairs used by different people. Okay, this is the Fourier transform pair used by control system engineers and signal processing engineers. So those who study signal processing, and this is being taught as a part of signal processing. So this pair is used by people who study control system and signal processing. But there are three other pairs, namely one particular pair for those who study quantum mechanics. In quantum mechanics, people do Fourier transform, but with slightly a different pair. Okay, what do I mean by pair? For example, from this integration. Okay, who gave me an idea of putting this 1 by 2 pi outside? I could as well put this 1 by 2 pi inside here and do away with that, right? So yes, it basically depends, and these two terms are again identical, right? E to the power minus j omega t. I could interchange these, right? So with those interchangings and bringing this pi inside or outside, okay, we have three more pairs, and again the frequency is radian per second. We have three more pairs, okay, which we don't need to study right now, but we need to know about. Okay, one pair is in particular used by people who study quantum mechanics. In quantum mechanics, Fourier transform is quite ubiquitous. For example, they study wave functions, and wave functions are nothing but signals in our terminology. So they do need Fourier transform, but they use a different kind of Fourier transform pair. People who study pure mathematics, okay, Fourier transform actually comes from a completely different perspective, and they have a different Fourier transform pair, but they would mean the same thing eventually. Okay, and people who study communication engineering, they represent everything in a similar fashion, but only difference they make is that they express everything or the frequencies not in radian per second but in hertz, because of course in communication engineering everything is talked about in hertz, not in radian per second. So with that said, we have three other possible pairs, but this is a pair. So this is the Fourier transform pair used by control systems and signal processing engineers. So if you are studying signal processing or doing signal processing, or if you are doing control system engineering, and if you need to use Fourier transform, okay, you can look through any book and any material on these subjects. They are highly likely to use these expressions. There are three other pairs which you shall not be discussing in this. Okay, but nonetheless, the idea is identical in nature, and as long as you are consistent with what you are using, you have a correct result. You shall always have a correct result. Okay, so that is what we have discussed so far. So we have actually today we have seen where Fourier transform actually comes from. So Fourier transform comes from Fourier series, a generalization of Fourier series. Again, the Dirichlet conditions must be satisfied by the signal in order for a Fourier transform to exist. But for any signal that has a periodic in nature, has a Fourier series, and if the signal has a Fourier series, it must also have a Fourier transform. But in order to have a Fourier transform, the signal does not need to be periodic. The signal can be aperiodic, and the signal can still have a Fourier transform. Fourier transform is nothing but a generalization of Fourier series. So this is what we have discussed today, and thank you for being in the class. This has been a slightly more mathematical class than our usual scenarios, but I hope that I have explained things adequately. And again, if you have any query, feel free to ask. I'll be here for 5 more minutes. Feel free to ask if you have any query regarding anything. And we shall be scheduling our next class on on Friday, and there we shall be solving plenty of problems. So don't worry about problems. So we are basically going to need 2 more classes on Fourier transform. So today we were supposed to talk about these, but we couldn't. So let me get rid of these. So we shall be solving and talking about the properties on the next classes. So we shall be needing 2 more classes. Okay, so with that said, if you have any query, please feel free to ask, or you can mail me your queries. And yesterday I sent you a worked out example on convolution. I think you people got that. Right. So with that said, we shall be ending our discussion today. Again, if you have any query, feel free to ask. As usual, this video will be available after the stream, and I shall be sending you the handouts. So yeah, thank you very much. Thank you. See you on Friday.